that my batch gold medalist is going to speak. So I immediately got a lot of response that, okay, so that means you know very big people. I said, yeah, I know. And there will be quite a few of them joining. Abhay Deshpande and other colleagues, Professor
One
Krishna.
person is giving a lecture.
So
One
sure
person
you will
is giving a
enjoy.
lecture.
Yeah.
Professor Ramurthy.
I'm
Hello.
very honored
See your
that Professor
picture.
Ramurthy has joined.
Yeah, I see your picture, but not you in reality.
Well, I will try to see whether I can switch on my camera.
Yeah, it's been a long time since I saw
After
you.
a long time, you have not changed at all, except all your wisdom is oozing out as white hair.
That I'm not sure.
That's
Good.
a bit serious.
Not serious. It's very serious.
No, and he has uncurled his hair.
After a
I think.
long time.
Uncurled.
Yes, almost 30 years before I met, I think you.
Yeah. Even longer, actually.
Yeah, good.
So how,
Professor Ramurthy, you have met me also as Raghav Verma's wife.
Oh, you are in Bombay University now?
I am the head of the department right now. I am going to start the UoM.
Oh, I see. Okay. I didn't realize that.
Yes, so I sent you a chat message, probably you didn't see. I also met you about 30 years back.
Good to see. This is a very good occasion.
Warm welcome to you, sir.
hey, hello, Alok. क्या हाल है?
Hello, how are you? Naveen,
Very
nice
good with you. सब ठीक है?
Yes, fine.
पीताम्बर जी, आप कहाँ पे हैं? Where are you? I can't hear you.
Who?
Pitaambar ji, your mic is off.
Yeah, I am at home now. I have retired.
Yeah, but home is where? Bombay or?
New Bombay, New Bombay.
Okay.
So, Chetan sir, shall we start now?
Yes, madam. We are already live now on YouTube.
We are live on YouTube.
Can you tell me how many students are there who are watching? Any idea?
I think they are going to join slowly after the university song is over. So they'll come by 4:45.
Yeah, let me also
You
check.
have
Maybe they
joined
are
also.
engaged with something else. Then we'll ask other faculty to release them. So by the time this program properly starts, students should be able to join. I'll just check on that.
Dr. Amrita, can you send a message on the group?
Yeah, I have sent the message and I'll check again.
Thank you.
On Zoom, there are 35 people, and right now some 5-6 people are joining.
Naveen,
Yeah, बोलिए.
don't worry, you give the lecture. I'm keen to hear you.
अरे यार, Jain साहब, this is all this is undergraduate stuff that you're going to hear.
Whatever
So
it is, I'm still keen to know.
But वो सब फ्रांस से आ रहा है ना भाई.
अरे यार, पंचादा साहब, physics तो universal है ना.
Good. So don't
चलो
lose
शुरू.
your enthusiasm.
Yeah,
There is always something new, so we are looking forward to it.
yeah, I hope I can keep your interest.
नींद आ गई तो मैं सो जाऊं.
No, बीच में जगह दूंगा. कब मैं बात करता हूँ, it's not possible to sleep यार. उसमें chance ही नहीं है.
चलो ठीक है.
Not because of the gyan that I'm giving, but because of my voice.
Yes. If Naveen talks, no one sleeps.
That's it. Yes.
So shall we start now?
Yeah,
Madam, yes, I think we can start. A few students have joined. I think they are joining slowly. So
by the time the song is
So
over, I think.
चेतन साहब शुरू करो, फिर song होगा तो तब तक.
Okay. So let us then start the program. So good afternoon to those of us who are joining from India, and good morning, good evening to those who are joining from outside India. A very warm welcome to all of you on behalf of the University Department of Physics, University of Mumbai. This is the 30th lecture of the GYAN-Series, which is the Golden Year Alumni Network lecture series. This is celebrating 50 years of the establishment of the Department of Physics. So today we are very privileged and honored to have Professor Naveen Alahari, who is the director of GYAN France, with us as a speaker. Before we begin the program, it is our tradition that we listen to the university song. So I'll request my faculty colleague, Mr. Chetan Gurara, to please start the song. Thank you, Chetan sir. I'll now request our head of the department, Professor Anuradha Mishra, to deliver the welcome address. Madam. Hello.
Anuradha, we can't hear you.
Am I audible now?
Yes, ma'am. Yes.
Yeah. So well, esteemed speaker, Dr. Naveen Alahari, all the distinguished scientists from BARC, Professor Ramurthy, we are very honored to have you with us here today. All my respected senior colleagues from the university, from other institutions, BARC, colleagues from the department and campus, and our most dear alumni who have joined us today for this meeting, and all my dear students. It's my proud privilege to welcome you all to this 30th session of the GYAN lecture series. Since many of the distinguished guests have joined today for the first time, I take this opportunity to say a few words about this GYAN lecture series, although at the cost of repetition for the rest of you. GYAN stands for the Golden Year Alumni Network, as Ritika mentioned, and it is the name of the alumni lecture series of University Department of Physics, which was started to kick off the Golden Jubilee celebrations of University Department of Physics in online mode. May in 2021, we have completed 50 years. And for the last 12 months, with the support and participation of our alumni, we have been continuing this series. The series was inaugurated on July 29th by a lecture by Dr. Anil Kakodkar, who is not an alumnus, but he led the autonomous department as the first chairperson of our board of management from 2014 to 2017. So Dr. Alahari, we became autonomous in 2013, and Dr. Kakodkar was the first chairperson of the board. He delivered a talk on higher education and national development on this occasion. His lecture was followed by a number of talks by notable alumni of the department who had graduated from different decades. We had speakers from all decades, all 5 decades, speakers working in diverse areas and located in different parts of the world. All these talks are uploaded on the YouTube channel of GYAN, which is being maintained by my colleague Chetan Gurada sir meticulously. Among the talks that were delivered in this last 1 year, we have heard eminent researchers who are alumni of the department in the areas like high energy physics, astrophysics, astronomy, neurophysics, condensed matter physics, nuclear physics, material science, medical physics, accelerator physics, atomic physics, space physics, and atmospheric physics. We also heard a number of talks from other alumni who have delved into territories other than traditional teaching, education, and research, and who have made a mark for themselves as successful entrepreneurs, business persons, science communicators, medical physicists, and in one case as Deputy Director General of Geological Survey of India. We also heard from a couple of relatively younger alumni who are committed to the cause of science and social outreach. There was a wide range of spectrum in the themes, in the age group of speakers, and also in their geographical locations. We had speakers from Jammu to Trivandrum and Chennai, from Kolkata to Mumbai and Pune in India, and we had speakers from abroad, 3 from USA, 2 from UK, and 1 is from Brazil, Australia, Austria, and Taiwan. Today we have this 30th lecture of the series, again by a very distinguished speaker, Professor Alahari, who is the Director of Grand Accelerator National, the IONS Louvre, better known as GANIL, situated in France, which is a leading research lab in the world engaged in research with ion beams, not only in nuclear physics, but also in interdisciplinary areas involving atomic physics, material science, and chemistry. As we are all eagerly awaiting to hear more from Professor Alahari about GANIL, I welcome you all to this 30th session of the GYAN series, and thank you for joining us.
Thank you, madam. Now it is my great pleasure to formally introduce our speaker, who actually needs no introduction for us, but for the students, we need to do this. So as we have already heard, Professor Alahari is presently the Director, the Grand Accelerator National d'Ions Lords GANIL, which is in Caen, France. He joined the CNRS, which is La Centre National de la Recherche Scientifique, as Director de Recherche in 2004, and has been working at GANIL, Caen, France, since. Prior to this, he worked in India for 17 years at the Nuclear Physics Division of Bhabha Atomic Research Center, working at Pelletron Accelerator Facility TIFR. He spent 2 years at the National Superconducting Laboratory at Michigan State University on sabbatical while in India, and a year sabbatical in Tokyo Institute of Technology, Japan, while in France. His research career over the last 35 years has been a continuous quest to measure and understand both the reaction mechanism and the intrinsic structure of nuclei and their interconnectivity. These explorations have been carried out over a wide dynamic range, spanning energies from well below the Coulomb barrier to 250 MeV per U at facilities in France, India, USA, and Japan. Professor Alahari is the recipient of the Joliot-Curie Prize for 2016, awarded by the French Physical Society. A warm welcome to you, sir. So I would like to now hand over the mic to you, and thank you very much for coming.
Thank you. Can you see my screen?
Yes, yes.
Okay, so firstly, it's a great honor and pleasure to be here back where I started nuclear physics in a way, and to look and meet all my colleagues. Unfortunately, I can't see the students, but so before I start, I would like to apologize to my senior colleagues that this lecture may not be very useful to them, but I hope it will be useful to the students. So I have prepared it for according to the information I was given, that so I talk to students mainly. So what is the plan of my talk? So I will go back to the future, that is about my days at UDP, and then I will give you some little GYAN, and then I will give a very long introduction to the field. Then I'll talk about GANIL, which will include a virtual visit and give a couple of examples of experiments, and then talk about our new superconducting linear accelerator, and then I will summarize. So let's start at the beginning. So in UDP, I was there from 84 to 86. But I start with St. Xavier's College, where I was, because the first time I came to UDP was when I was there, I mean, when we finished, and it was very interesting because there were 5 of us who came, three guys and 2 girls, and we were just entering the canteen and somebody said, these guys are from Xavier's. Till today, I didn't understand how the guy figured it out by looking at us for 1 minute. So that's why the St. Xavier's College is there. So it looks like a long, long time back. Yes, but I'm still alive and kicking. So to go back in history, so I had chosen at that time the choice which was called NP1, which was theoretical nuclear physics, because I was sure that I was not going to do theoretical nuclear physics, but I was going to do experimental nuclear physics, and it was very important to have a strong basis, and which was excellently given by my professors here. So I spent a lot of time in the lecture theaters, unlike many of my colleagues at that time, because this is where we get GYAN from, is from professors. And then just to name a few, so I was just thinking a lot when I was trying to prepare for this talk, and then of course all these names came up to me immediately. And then I don't know, maybe some of the students might not know some of them, because I'm not sure if they're still teaching here. And then I just had a chat with Professor Angwala just now, and he still remembers me, so I'm greatly honored by that. And in addition to that, there's one thing which, since Professor Angwala is there, he used to teach us one of the courses in the second year. And his writing, as you probably know, is so beautiful. And every time he rubbed the board, you would feel such a tragedy, because some real, artistry was being removed. And then I spent also a lot of time in the library, which is also great fun. And then, of course, in the canteen. Recently, I was looking at that in the newspaper somewhere that they were complaining about the price of the food in the canteen. But when we were there, it was extremely cheap. In addition to all that, we also played a lot of cricket and also table tennis. So overall, the stay at UDP was great fun, learned a huge amount, and it was wonderful. Then from there, thanks to all the training that I got, I joined the 30th batch, which is coincidental. I give the 30th talk, and I was in the 30th batch of training school. And as was mentioned, I was in nuclear physics division and I worked at the BRC-TFR Pelletron Accelerator. And then also I made some sort of world tour, and today I'm at Ganil in France. So being in UDP, one gets a chance to go around the world, not in 80 days, but keeps going on, and everything starts here. So just to remind you that, okay, as it was said, I spent a long time in India, and that is where I learned everything. Okay, the real Gyan came to me in this place, including my St. Xavier's College. And then this Gyan which I got is what I used here. And believe me, this is my foundation of today's, where I am today is based on the Gyan that I got here from my professors, some of them who are here, and all my other senior colleagues and younger colleagues who are here from NPD and other places. So this is for the students, of course. So now on, I only talk to the students and I forget my senior colleagues. So it's always good to be clear what you have to get from this talk, okay? So the take-home question are, one, there are no stupid questions, there are only stupid answers. B, there are some questions that cannot be answered on Google. And 3, choose a job you love and you will never have to work a day in your life, okay? So this one especially is very important, the Google part, really. That's why we have professors. So now let's probe at the different scales that we are, and all these scales, except the last one, were covered at UDP. So we start from the discovery of the nucleus. Then we have bulk matter, we have atoms and molecules, we have then the inner structure, which is the nucleus, which I'll be mainly talking about today. And if you look deeper, you have the quarks and gluons, and then if you look deeper, you stop at the quarks. So that is their fundamental. And nuclear physics, which is the quark-gluon plasma, it was also done at CERN, which I will not be talking at all today. And even though we are talking about a scale of nuclear physics, there are still signatures of the quarks in the nuclear physics that we do. So then, just to also set the scale correctly, so today, so this is generally the mass scale. So today the syllabus that will be restricted is to below particle threshold. That means we just talk about neutrons and protons. We do not create particles. So this is be a very restricted talk in that sense. So let's start at the beginning. So as you know, the nucleus was found in alpha plus gold and scattering. But if you go and look up the original paper, you will find that they were done on many, many other elements. It was just not this. And it's only based on this that we learned about the existence of the nucleus. And this is the setup that was used with a 0.1 Curie source, which is an alpha source from 214 polonium. Many of these things you will not be able to do today because of radiation safety. And if you go and look up the original experiment, you will find that it is a real challenge. And things like, because it was a screen that they were looking at, and they had things like, so that because the eye was getting tired, they would look away and then come back. It's incredible, and it's really worthwhile to look at this original text. So what did they do? We all know that this was Geiger and Madsen who did all the hard work with, and Rutherford was the advisor. And then the question you want to ask there is, what is the energy scale? We talked about 7 MeV, okay? So then the question is, what would have happened if the energy of the alpha particle was much higher than 7.7 MeV? So just to say, this is a picture of Coulomb, and that's the basic answer. So the thing is, if you were above the Coulomb barrier, then you would be doing all sorts of complicated things. And as you know, that the Coulomb barrier is roughly given by this expression. And then, so what we see is this is the total, and this is what is called the height of the barrier. And this is a sum of the nuclear Coulomb and centrifugal forces. So these experiments like this we did at the tandem, and which are of course still, and the LINAC, which are being still done. And you can do a various amount of things depending on your energy, starting from, of course, elastic scattering, compound nucleus formation, inelastic mass transfer, and so on and so forth, depending on the energy and target projectile. On the other hand, if the the energy of the alpha particle, which Rutherford, Martin, and Greg used, then you would have got a lot of more complications. And then it would have gone into these various channels, inelastic scattering, transfer, fusion, which would be 201 thallium. And it would really complicate the analysis and probably would not have figured it out. And we would not have found the nucleus in that experiment. So then the other thing was about alchemists, and gold was very important, but the alchemist's dream in nuclear physics was to change one element into the other. And the first experiment, which was done again by alpha particles on aluminium, and it created phosphorus 30, and for the first time radioactivity. And this, the Nobel Prize in physics, in chemistry, was given to this in the recognition of production of new elements. So roughly what we do? So we have a as you know, we have a microscope, and higher the resolving power, the smaller we can see. So, and the accelerator does the same thing, and it gives you, so first it gives you the energy to overcome the nuclear repulsion, the Coulomb repulsion, and then one can get closer to see the nucleons. And higher the energy, the more smaller you can see. So this is just a typical example of a LINAC and some equipment at Ganil. So basically we have a beam. Okay, we can choose the energy, and then this, as you may be as you are aware, this beam goes in vacuum. And this, what I just show, is one type of vacuum pump, which is basically, it looks like a jet engine, and it runs, these vans run at 36,000 revolutions per minute. And this is called a turbomolecular pump. And then in Ganil, the speed of the beam is roughly 1/3 of the speed of light. And we have particles, number of particles, which go typically from, let's say, 1,000 to 10 power 13 to even more, 10 power 16. Then, so what do we do with this? So we need to make some nuclear reaction, and then we need to have a scales. So the scales of our reactions are at the level of 10⁻17 to 10⁻21 seconds, depending on what reaction we look at. And the scale is, of course, at the femtometer scale. So here what I show you is actually a photograph of real events in an experiment. This is a very special detector. It's both the detector and the target. It's called active target. And here you can see the beam coming in, the interactions occurring at different places. So different places corresponds to different energies. So you can measure an excitation function and do many, many things. And an equipment like this was used to discover hydrogen-7. And then the other thing, as the experimentalists, we should all know, there are two things, and they're not the same. There's one is precision and one is accuracy. And we need to be both precise and accurate, and I will let you think about it. So let's start at the beginning. And as I said, modern alchemists are no longer chemists. They only are nuclear physicists. And this is the Mendeleev periodic table, which we celebrated the 100 years very, very recently. So what is the question that we ask here? The question that we ask here is, how many protons can a nucleus hold and still be stable? So today the answer is that we can have 118 protons held together, of course, with the neutrons. Then the quest that is going on is for 119 and 120. And just to tell you how difficult these are, so our colleagues in Japan at Riken got one count of 113 NH, which is nihonium, which is the Japanese name for Japan. And they got one count in 6 months of continuous running. So you can imagine, as you go along higher and higher, gets more and more difficult. But of course, our colleagues come up with more and more interesting and innovative ways to get there. Then, so I just give you some basic definitions, which you may be knowing, but I would just like to repeat it. So time to time, I have some focus, important, very open, very important, because we all know that it's very difficult to stay awake all the time in a lecture, but time to time you need to be awake. So whenever you see something red like focus and all, please wake up. It might be of use. So basically what we call nuclear far away from stability is we have things which are here. So in this direction, we go in Z, and this direction we go with more protons or less neutrons. And this way we go to more neutrons. So the idea is that And this is what I call super heavy. That means when we go to Z greater than 104, we go in this direction. So basically that is when we go away from stable elements, basically that is in either direction, you always come back to stability either by emitting beta particles, alpha particles, or split through fission. So this is some just shown for mass number 137. So you can see you finally come back to the stable nucleus. And then, as you know, and you would have learned in your course by now, the binding energy per nucleon is roughly around 8 MeV. So this is a number you need to know, remember. And then the thing that is important just to remember is about drip lines. Now, what is drip line? By the English word, you realize that the nucleon or proton can just go away. So what two important things that are to be remembered is what is one neutron separation energy and two neutron separation energy, which means what is the energy required to remove one proton or one neutron. As you know, near stability, it's around 8 MeV, very roughly. So this is how it is defined based on the binding energy formula. And the idea is that if the separation energy is positive, then the nucleus is stable to nucleon emission. Please note, we are not talking about beta decay or alpha emission at this stage, but we are talking about nucleon emission. And if the separation energy is negative, the nucleus is unstable. So what is the definition of drip line? Is that when S1n is equal to 0, it's called the 1 neutron drip line, or S2n is 0, it's called the 2 neutron drip line. So basically the nuclear existence ends at the drip lines where we don't have enough binding energy to hold them together. We can have resonances and other stuff, but this is what we call as existence, and I will come back to it again later. So now we can design my own nucleus. So the question is, as I said, how many neutrons can you add or remove from a specific element and still be stable against particle emission? So first we need to find out what these are. And of course, then we always have to do why. So I just take one element, which is carbon, Z equal to 6, which has two isotopes which are stable, carbon 12 and carbon 13. Now the question you want to ask is, I keep pulling out neutrons because we don't, if we pull out protons, we will change the element. So we remove neutrons, and then you will find that these things in the blue are stable. That means they live basically forever. And as you keep pulling out neutrons, you find that the lifetime keeps going down. And here at carbon 9, it comes to the lifetime is 0.1 seconds. Now the point is that if you pull out one more neutron, it doesn't exist in the sense that it is the binding energy cannot be held, and carbon 8 is no longer stable. Then you ask, then I keep adding neutrons, and you can see this is also partly stable. You can find that again, you can go on till 18 and it is 0.09 seconds. So it gets shorter and shorter. Now the question you want to ask is, how far can you go? Can you just keep on going, or is this the limit? So in this case, in this specific case, it ends at carbon 22. Beyond that, a system of carbon 23 cannot be held together and be stable. But you'll also find funny things like that carbon 21 doesn't exist. Okay. So the first goal was to measure this, that there is nobody here, and where this ends. Okay. And I said, and then we have to figure out what is going on. So then the question is, we talked about carbon, but we have the whole periodic table. So we want to know how many isotopes are possible. Basically, when we say possible, what we have to be clear is that when we take a projectile and target, we can always make anything you want, but they live for too short a time. So the definition in just one way would be that the atom should live long enough to be able to chemically react, otherwise it doesn't make sense. So then this discovery of new isotopes is very closely related to the production and basically to accelerators and also to reactors. So in this way, you find that every time there is some breakthrough, you will find many more isotopes which are discovered. The elements are not so easy. Here we are talking about isotopes. Then we come to the Segre chart. which you know is the plot is now, it's a two-dimensional plot of the isotopic of the Mendeleev stable. So here the direction of number of Z, the number of protons, and this is the number of neutrons. And you can see that the black stuff here are the guys who are stable. So there are around, let's say 290 such elements which exist on Earth. And as you keep going away, then there is a limit before which they do not exist. So now that's what I call this drip line. So basically, if you go beyond a certain number of neutrons, they are no longer stable. Okay, so now the question is this number, we only know today till fluorine. Okay, so we do not know what the drip lines are beyond fluorine. So as you can see, there's a lot of work, and there's a lot of work for you guys to do when you join this field. And then the question is, okay, we don't know how much it is, but then our theoretical colleagues are always there. So there are 3,000 known today, and only 1,500 with some detail that we know. Okay, so now we can keep going. And then the question is that there are many that are predicted. So today it is predicted to be 7,000. This depends on the theories. It could be 8,000, but basically the point is that we are very far away and there's a lot of things to still find. But you have to be careful. I mean, every isotope here cannot be interesting. Some are more interesting and some are less interesting. So when you do this search, you have to be careful and you should look for the important ones. So for example, I took stamps. Okay, so you find this here, this is of Lincoln. This costs around 0.14 million. Then there is something else, which is 9.5 million. Okay, so when we are looking for this nuclei, it's very important we choose the right region, the right isotope, so that we can get the maximum information that we want, whatever it is, by choosing this nuclei. Then the question that you want to ask is that when you go away from stability, are their properties different or they just remain the same? We just have more neutrons and less neutrons. So then if I just focus on the lower part of this Segre chart, so starting from hydrogen to fluorine, by just looking at this, okay, you will see that there are some funny things going on. So you find these gaps, which I talked to you about for carbon. I told you 21 is not there, but there are other such things which go on. So then the question is why? And then as you go, there's another nice thing is that as you go from carbon to, let's say, fluorine, normally you will see as you increase the number of protons, the number of neutrons also increases. But when you come here, you find that you increase the number of protons, but the number of neutrons doesn't change. So this you can call something like the Bermuda Triangle. So first is to figure this out and then to see why this happens. So then I told you that as we go away from stability, are the properties different? So this is lithium-11. So when we go from lithium 6 and 7 are stable, then you keep increasing and then you come to lithium-11 and it starts to look like this. And normally what I expected just that this size increases, but then something very funny appears and then it looks like that. And then if you look at this, you will find that lithium-10 is not stable. So lithium-11 is called a Borromean nucleus. That means, as most of you would have seen these 3 rings, when you remove one ring, the other 2 are not held together. So lithium-11 is something like that. So you remove one neutron and the other 2 are no longer stable. And there are many nice fun stuff like this. Then the other thing is which you have learned at some stage in your life is the nuclear shell model, which is for which the Nobel Prize was given to Maria Mayer-Gopert and Janssen. So there you know that you have learned about these shells and what you call magic numbers. By the way, magic number, which means that magic means you don't understand. So it is not true. So what we need to call them is shell closures. So the thing is, this is what we have 2, 8, 20, 50 and so on. And this is what we know near stability. Now the question is, does it become, when we go away from stability, does it remain the same? So for example, this is just one that we show, that n equal to 16 becomes a thing and n equal to 20 no longer is a magic number. And in addition, as I said, we started with the binding energy near stable nuclei, which is around 8 MeV. And as we go away from stability, this binding energy becomes almost 0. So when it becomes 0, we get very close to the continuum. And then we have to take into account other important things, which is coupling with the continuum. And now we can call them open quantum systems, but we don't need to get into that. So then, as I said, we have funny things going on. So lithium-11, which looks like this, is roughly, can look at the size of calcium. And so when you go to other nuclei, you will find that they become bigger and bigger. I mean, when you're far from stability. And so this is something which is unexpected. So for example, you look at the lithium nucleus and you look at the radius of these isotopes, you'll find roughly it goes like this. Let's not go into details of this because there are already some complications here. And then you'll find that the radius suddenly goes up, which is related to this, exactly what we see here. And such sort of nuclei are called halo nuclei. And this halo nuclei are just English words, okay? To be exact, basically what we call halo nuclei is when the last valence nuclei are at large distances from the core. And this is a better definition of this. And there's also something regarding the L in which this nucleon says. So just some pictures about this. So what we discussed are 2 neutron halos, but we also have 1 neutron halos like beryllium-11, carbon-19, and so on and so forth. So then we have all this nuclei, which I talked to you about, carbon-22, carbon-8. So we need to produce this, right? So first thing is to be produced, and then we can study what their properties are. So the basic thing is always, of course, you need an accelerator, then you need a target. And basically what you can do, you can come with this is very high energy, and you come and you basically do spallation reactions of the beams and also of the target. And then you produce short-lived nuclei, and then these can be post-accelerated. So this is something which is an ISOLD, which is a small facility at CERN. And then the other thing could be, you can come with neutron beams, and then you could just produce fission directly. And again, you could post-accelerate this, or you can come produce Bremsstrahlung or things like that. And you can also produce these short-lived nuclei, and which can be post-accelerated. And this, depending on the size or the method that you used, you can produce, you can go to different energy regions, and you can do different physics. So basically, each of these methods, I won't go into all of them, have different advantages. So, but basically what we are doing in all of them is we are producing beams which are of short-lived. That means, let's say, which range from milliseconds to microseconds. And basically these beams, before they decay, you need to do an experiment with it and then learn about these exotic nuclei. So what are some of the open questions that when we go far from stability? So the first question, as we already discussed, like we saw that there are existence of proton or neutron halos. So then you say, are these properties different from those who are unstable? Then basically the question is, what happens when you change the ratio of neutrons and protons? Where is the binding limit of binding? Then we discussed how do these shell closures change as you become more and more exotic. Exotic again is an English word. It just says when you're far away from stability. Then why do some nuclei have different shapes? They are not spherical. Then how does the structure affect when they react with each other? Are there new forms of radioactivity? And can we start explaining the properties of nuclei starting from quarks? Okay, there are advantages and disadvantages of this, but we can discuss that later. And then, of course, we all know that we also have to give back a little bit to society and what nuclear physics does. As you know, to do all these complicated and sophisticated experiment, we need high technology. And this high technology, which is developed for us, it goes out and is useful for the general public. And then, of course, we produce new isotopes for health, new materials, and we help how nuclear power can get even more safer. And more recently, we are using carbon beams to do hadron therapy to get rid of malignant tumors in our human body. So basically, what do we do in nuclear physics? We are exploring the physics of of infinitely small systems under controlled conditions. This is doesn't happen in all fields. Here, by changing the beam energy target projectile, we can do a lot of stuff. So we have a lot of freedom of studying these quantum systems, and then small quantum systems. And then the good part is that we do social service, that by understanding physics of the infinitely small, we can also understand physics of the infinitely large, basically for which are about the formation of the universe, what are the reactions which go on stars, and so on and so forth. And this is very important to understand, that we do nuclear physics or any other field because it's interesting and because we want to understand it. And we are not here to explain it, not here to serve other communities. We are serving other communities for free, but our goal is to understand what we are doing. Okay, that means the subject itself and impact is for free, because many times people think that we justify our field by showing that we are useful to other fields. This should never be the case, because we believe in what we do. So putting it very simply, nuclear physics can be looked at the moment, as you know, in XYZ. Once we have the coordinates, we know where we are. So similarly, historically with nuclear physics, we started with the accelerators which put in excitation energy, or we heated up the nucleus. Then historically, it was the heavy ion accelerators which came in, for example, the one at the pelletron at the BRC TFR pelletron at TFR. So then we brought in a lot of angular momentum. So basically we started to spin. Then what we just spoke about previously about nuclear far from stability. So this is the isospin. So basically we change the ratio of neutrons and protons. And then we look how the properties of the nucleus change in this phase space. So by mapping out this phase space, we understand how the structure of nuclei evolve and how they behave. Basically, as I said, we do it through nuclear reactions. The time scheme we have already discussed, the different types of reactions that occur. And as you keep increasing, we start from fusion fission, then we go on to multifragmentation, and then we finally go on to vaporization. And this depends on the energy that we use. And then the other thing we have to learn is that things have to be always simple. Okay, so what you see here, don't go into worry what it is. Okay, this is excitation energy, is angular momentum. It's not important. So these are some of the measurements that we make. And to you and to us, it's boring. You say, what are these silly things? So the goal always is to look for simplicity. And finally, so the product of all this, when you understand what really this picture means, it tells you what is the shape of the nucleus. So basically, one of the key questions is, by understanding how regular and simple patterns emerge in the intrinsic structure of the complex Benny body of the nuclei, is what we want to understand. And this is one of the key questions. The second one is, so depending on the structure of the beam, whether it's a halo nucleus or a strongly bound nucleus, or the target is some different thing, we want to identify the degrees of freedom which will govern the collisions of these nuclei. So for example, the eagle, which we can take as a projectile here, would interact differently with something if it had one fish or two fish or no fish. So basically that's what we are talking about by degrees of freedom. So, and then of course, these two are intimately connected, and we need to understand both, otherwise the understanding is not complete. And so this, what I've shown you here, is nuclear physics in a nutshell. But you have to remember, to do this in a nutshell, all that we are being taught at university and later is required. Otherwise, you will not get this. So please remember that everything that we are taught at UDP and later, many of the times you think, why the hell am I learning this? But I can assure you, everything will be used somewhere. So please do your best and listen to the profs. So then just to tell you where my lab is. So this is France, and we are located here. That is, so if you expand here, this is what is Caen. And Caen is known for it's very important because it is where the D-Day beaches are. The D-Day beaches are around 20 kilometers from Caen. So this is where on the 6th of June of 1944, the Allied forces came in and liberated France from the German occupation. So Caen was fully occupied by the Germans. So then now I will speak to you about GANIL and give you a couple of examples to discuss what we mentioned earlier. So what is the specialty of GANIL? So in GANIL, we have 4 types of beams. So we have the stable beams, which I discussed, is around 290 of them are available. So in principle, we can take any of these beams and accelerate them and use a nuclear reaction to produce nuclei or to understand how they interact. Okay, we have both cyclotrons and linacs here, as I mentioned earlier. So these are charged particle beams, which also include ISOL, radioactive ion beams. So this is, don't worry about what is ISOL. So basically you produce, as I mentioned before, you come with a beam, hit a target. Okay, you heat up this target, you get these short-lived nuclei to come out of the target, and then you reaccelerate this. So all this process takes a little bit of time. So the beams that you can get have to have lifetimes at the level of milliseconds. But if you want to go to shorter-lived nuclei, then you come, just bang a high energetic beam on a target, a thin target in this case, and then you get beam-like products or target-like products which are flying, and then you use these beams to hit the target and do whatever science you want to do. And then we also have fast neutron beams. Okay, so you can also do experiments with these beams. So, and of course, with all these beams, you need state-of-art instrumentation. And we, of course, need you and other scientists to find out what is going on with this. So these, as I said, is microsecond, millisecond, and this is infinity. And this, okay, is fast neutrons, is just free neutrons, is 818 seconds is the lifetime. So then we do a nuclear reaction. We have to use various complicated detectors. Then after we do all this and we measure things, the measurements we make are actually very simple. They just include what are the types of particles coming out, what is the energy of these particles, what is the angular distribution of these particles, and what are the correlations between these particles using complicated detectors or simple detectors. Then we build a simple theory. So here is the question of a spherical cow, which we know it is not, but we start from simplicity and then we build up our models. And the basic goal from our models is that they have to have predictive power. So we cannot create a model for each nucleus or each phenomenon. And then that is when we learn, and then that's how our understanding grows. Okay, now I just tell you what GANIL is. So GANIL has a set of 5 cyclotrons, and we have beams starting from 0.3 MeV to 1 MeV per nucleon just by using the 2 ion sources. Okay, so if we don't send it into our 2 cyclotrons, we can have these low energy ones, which are used for condensed matter physics or other non-nuclear physics stories. Then you can go into one of the cyclotrons, and then you can come out only using 1 cyclotron. And here we can go to a range from 13.7 to up to 13.7 MeV. Again, you can do a different type of material science or even nuclear physics out here. Then if you further want to increase the energy, you go through the 2nd cyclotron. So basically you need 1, 2, 3 cyclotrons to get around heavy ion accelerated beams. And that will be 95 MeV per nucleon. So if you have a beam of carbon, it will be 95 into 12 would be the energy. So that would be roughly 1.2 GeV. And then we have various experimental halls where these beams can be used. Then in addition, you take this heavy accelerated ion beam, you go and hit a target here, you produce this elements which isotopes which are interested, and then you reaccelerate these and then send it to these experimental halls. So this is what I called before the ISOL. This is isotope separation online. So here then so we do some jugglery here, chemistry, and actually here magic, because chemistry is much more difficult. You take out these ions and then reaccelerate it so you can define exactly the purity and the energy of these beams. And again, you do different types of experiments. So this is how GANIL looked in 1978. It was built in the middle of the fields and there was nothing there. And the first experiment was done in 1983. And these are the cyclotrons from the inside. Then in 2011, a new accelerator was started to be built, which now is in the final states of its commissioning. So unlike the cyclotrons, This is a linear accelerator, which I will come towards the end of my talk. And here you can have heavy ions till the energies of 14.5 MeV. And you can have beams starting from protons to two heavy ions, but proton, neutrons, alpha particles, which actually are not allowed in Ganil due to radiation safety. Because if we wanted to use these light beams, we needed to make the concrete barriers higher. So here we have the LINAC, which can give these heavy ion and low ion beams. So this is how it looks. We will look at this later on. And this is how we started. Spiral 2, the LINAC, is 9.5 meters below the ground because the intensity is so high. If you want to shield, it would have cost a fortune. So therefore, it was built underground. And the whole facility looks like this. There are new things which are coming up, which I'll discuss towards the end. And then there is some other plan which was to couple this, which is basically on hold now. So now I will give you a virtual tour instead of showing you pictures. So because the picture is 1,000 words. Okay, so this is how Ganil looks from the outside. So this is where the cyclotrons are, and this is where our cooling plants and other things are. So now let us enter inside. So this is where our control room is. You can see the cyclotrons here and the various facilities which we will visit few of them. So this is how it is. Then this is, as you can see, it's empty. It's taken when nobody is working. Then we enter the cyclotron ion sources. So there are 2 ion sources on each one. And what happens is that when we are preparing the beam for one of them, the other one is sending beam into the cyclotrons, or it can send low energy beams directly, the accelerated only by the ion source, let's say till 1 MeV per nucleon, and directly to this hall, which is used, as I said, for material science or condensed matter. Sorry, did somebody say something?
Are you playing a video? Because
No, I'm not playing a video. I'm just, oh, it's a video, is it?
You're
yeah.
just stuck at the slide. We are at a...
Oh, I'm sorry. Oh, it was me. Oh, I'm very sorry. I will go back. I'm sorry about that. Yeah, I should have changed the share. So I'm sorry. I just come back. So I was talking about the cyclotrons. So we enter here. Now, can you see the video?
Yes.
Yes.
Now,
Yes.
Yeah. So I'm sorry about that. Sorry, I didn't realize I changed the screen for myself and not for you. So this is the control room, as I just said. So I won't repeat too much about it. So this is where we control all the accelerators. Then what I said, we go to the ion sources, which are 2. And then I said, this is the experimental hall for low energy, condensed matter or material science. So then we come back to where we were. Then we go to the cyclotron. Okay, so this is the first cyclotron out here. And then we can go. So there are 2 such cyclotrons. And then finally, at the end of that, we can go to what we call the fishbone. So the beam comes in from here, and depending on which beam hall that you want to go to and you want to do an experiment, you can go there. So for example, just a minute. So one of that would be here is this is one of the experiments which we will talk about later. This is, you see some of the germanium detectors, and behind is the spectrometer. So I come back here. I'll go back. Sorry. Oh, sorry. So you can see the shielding all around. Okay, now I have to find the other guy. Sorry. Okay. Get lost myself. Yeah. So this is where we produced these beams, which are produced, which have a lifetime around around microseconds, and then the beam is produced behind here. It comes out, And you can, so this is what I call the active target. The beam comes in, this is a gas detector. So it acts both as the target and the detector. And it has around 10,000 channels, which you process to get whatever information that you want. So, sorry. And then just to give an idea of another experimental hall. So this is called the Indra Fazia. So the Indra is, yes, our Indra, the king of gods. So there was the person who worked on this was an Indophile, and he knew everything. In fact, the subroutines are in something called Kali Veda, and each subroutine is called a Veda. So this was let me get back. Yeah, I think this is a tour of the cyclotron. So let me go back here, and now let me go to the Spiral 2. So again, this is the control room of the LINAC. Today, we have made both the control rooms into one. So then again, we go into an ion source. Okay, it doesn't, so we somewhere the sample that you want is put, and then it's here, in fact. And then in this case, you produce a plasma, and then you get out the things you want, and then you put them into the linear accelerator. So you start with the radio frequency quadrupole, not important. It's an accelerator which is a small accelerator which also focuses, and it's followed by the by the accelerating cavities. Okay, each one of them accelerates the ion beams in certain way. We can go into it, and they all are at liquid helium temperatures, and which are produced in-house, and you can do whatever you want with these things. Sorry, then let me go back. Then sorry. And at the end of the accelerator, you can go directly into the beam dump, which is out here, which once we start running, we cannot enter because the intensity is so high that it has to remain closed. And then one goes to the Neutrons for Science experimental hall. Okay, so where the beam comes in from here, there's a lithium or a beryllium target, and then you can produce the neutrons, and it goes into the other room where you can do experiments, and I will come back to that. So let me stop this and let me come back to the talk. Sorry, can you see the slides now?
Yes.
Yes, yes.
Okay, so this is what I just finished. Okay, so let's go to the next one. So as I was saying, so we have energies starting from very low energies, a few kV per nucleon, to 95 MeV per nucleon. And depending on the energy that you have, as I said, you can do a lot of condensed matter material science, and we can go down to the nano level even here. And some of the experiments are even study radiochemistry or astrochemistry, where they're trying to study the origin of ice in cosmic rays and things like that. Then we also do, as I said, something useful from time to time, is that we produce very fine filters which can go down to, which are very uniform. Basically, the polypropylene foils are irradiated by a beam which scans across the foils, and then it slowly rotates, and then you can produce these irradiated foils, which are then chemically etched, and depending on what you want, you can decide what is the pore size and also the interpore distance. And then this is used by different companies. Then we also do irradiation of components which go into space. And the idea there is because in space there is radiation, whereas in the lab and the radiation is very low. So in the lab, you can do that in a few seconds. So basically the idea is that you want to see what happens to these circuits under irradiation, and then you go back and you check other things, and you also get an idea of the lifetimes from such measurements. Then we also have measurements to see how you can produce certain isotopes like acetine, which are useful for radiotherapy, especially for tumors and other studies like this. So this is how the cyclotron complex looks. So we visited this Lee spectrometer. Then this is how this is where at the end of it, it was this. We also visited the Indra Fazia. Then we have other detectors. This is where the industrial applications are done. Then you also saw the ACTA TPC, which is the active target. Then we partly saw the array of detectors, which are the gamma array. And this is the VAMOS detector, which we didn't see, but one of the halls that we visited. So this is again the Maya detector, that is the active target. And then, as I said, it's all about making pretty pictures. So this is actually an in-beam spectrum of the Fuzia Indra detectors. So the beam comes in from here. These are the Indra detectors, which are back angle, and these are the forward angle Fuzia detectors. So basically they are charged particle combined with cesium iodide scintillators and also gas detectors. So with all this, you can produce interesting pictures. And these are the gamma ray detectors, which is called Agatha, which is a collaboration of 12 countries in Europe, because these detectors are so expensive that one country cannot afford it. And what you see here, the specialty of this detector is that it does gamma ray tracking. Okay, so it tells you when the gamma ray comes in, what is the angle it comes in from. So then this in some way is used for Doppler correction, which I will briefly discuss later. And then we have detectors, but we have to keep improving because you want to do more and more sensitive and selective experiments. So we can study fission, as I told you, we can do other things. And then we do also quantum tunneling, which you learned in your course. So this is a famous character in French literature where he passes through walls. So basically he's doing quantum tunneling, but he was doing quantum tunneling and stealing stuff. And here, as I said about the pictures. So what is this? This is Van Gogh's Starry Night over the Rhone. This costs around 65 million euros. And in Ganil, we make similar pictures. And don't worry what the x-axis and y-axis, I will describe it later. And you can see this is Ganil starts in a night shift. And believe me, this can be more expensive than this. So now let's get back to the beginning of the nucleus. So as I said, this was the size, to give you the size of the apparatus. These are, it is of this size. So where they discovered where did this experiment. Now, if you wanted, as we said, we add neutrons and we go until helium-8 to do the same experiment of helium-8 on gold. It took 100 more years. Okay. And as I said, this lifetime of this is 120 milliseconds. And to do this experiment, to produce this alpha 8 helium, we needed all these 4 accelerators, which I just showed you, to produce this beam. Okay, this also partly shows you why it takes so much time. But of course, helium-8 was discovered in 1963, but such experiments were only possible much, much later. So you do some simple experiments. So now I will take 2 experiments, which I hope are simple. So basically the experiment is helium-8 on gold. So you come with the 8 helium beam, you bombard gold. Then you can do many experiments, but I take an even simpler experiment, which you actually do in the lab. Okay, you look at radioactive decay. That's all. So you can, by knowing the nuclei which are produced, by measuring the X-rays and the gamma rays, you know which nuclei are produced. Okay, so basically what you do is you bombard the target. So that's what this is, the beam current. Then the products are formed till you stop irradiating, and then they decay. So this decay, when they decay, you put them in front of some detectors. In this case, these are high purity gamma ray detectors. And then you basically measure some gamma ray spectrum. And as you can see, because what we are measuring is very, very sensitive, I'll come to the number of counts that are produced are very, very small. So basically what you measure here is basically the room background. And what you want to look at is and if you look at for coincidences with an X-ray and gamma ray detector, because what you're doing by coincidence is that you're more sensitive, you remove out junk. And then when you do it with the target, this is how it is. So this is not it. So basically where you can see nothing here, you can get all this. And by measuring things like this, you can finally get the cross-section of interaction between, this is alpha plus gold, this is helium-6 plus gold. So basically it's the cross-section, how the cross-section moves as a function of the center of mass energy. and this is the binding energy, but we don't have to get into all this. So basically that when the question we asked is how do these how do these particles, when we change the number of neutrons, change? So you can see that in this case, it happens that these extra neutrons are basically sleeping and they're doing nothing. But in many other cases, they do a lot of things which are completely different. And as I was talking about sensitivity, here the measurement of 8 helium which we did was 6 orders of magnitude lower than compared to the beam that was here. So the beam of intensity for the alpha particles and helium weight was 6 orders of magnitude, but you can see that the error bars are comparable. So then I just go into, I think we are running out of time. So what we do here is we come by beam a target, we produce fission fragments here using a magnetic spectrometer, which is equivalent to, as you know, a prism. We separate out things in mass over charge. And then what we do is this is how it actually looks. This is what the Agatha, the position sensitive gamma ray detectors, and these are the exogam Clover detectors. So basically this length is around 8 meters. Okay, so the beam comes in from here, there is the target. So you measure the prompt gamma rays here, and then the residues of this are stopped here. And then you also look at the delayed gamma rays. So we produce around 400 nuclei. What you see here is a delta E plot, and each line here is a particular element. And then for each element, we have many isotopes. And then the idea is that what we need to do, DNA fingerprinting. So what is shown here is the mass number of the barium isotope, and what is shown here is the the decay of the excited states in this nuclei. And you can see where the bright one is where there are more gamma rays. And you can see that this looks like a DNA fingerprinting. That's what we do for ourselves. And here, this is what we are doing for the nucleus. And you can see as we change the number of neutrons, you can see that the energy levels are changing. And so we measure this for a great number of nuclei by going far from the stability, and we try to see how these properties change. Then I go to the last part of my talk is I go to the LINAC. So the LINAC the LINAC at Ganil is very, very special, is that we have very high intensity. To just give you a flavor, the intensity of this machine is 10 power 16 particles per second. Normally what we talk about is nanoamps, which is around 10 power 9 particles per second. Here we go to 10 power 16. And believe me, when you have such things, it's very difficult to have targets. But why do we have this intensity? Because we have high statistics. So then we can do more precise experiments, maybe accurate. Then we can look for rare searches and we can do everything. And then basically this gives you a chance for discovery. Doesn't mean that if you don't have this high intensity, you cannot discover things. You can also discover. So basically with this things, you can look for needles in a haystack and have more and more fun. And also it's very, very challenging experimentally. So this is how the LINAC looks. You already saw there was the ion source and the cryo modules. This is how the cryo module looks inside the superconducting cryo modules. We have 2 types and they accelerate for different beta, that is V by C. And then finally come out, we saw this, the neutrons for science. So the beam comes in, it breaks up the neutron beam into neutrons, and the neutron beam is what we use. And this is a collaboration between many labs in France and internationally, including India, which has contributed to building of this. And what you see here is what we call the LINAC CAT. This is actually a measurement of the emittance of the beam. Doesn't matter what it is, but it's something real. And again, you can always make pretty pictures. So this is how the neutron for science, you saw this in real, and this is how the neutron beam comes in here, and this is the neutron time of flight. So by measuring it at different energies, different distances, you can have different energies, and you can measure what you want to measure. So this is how the flux looks as a function of energy. So in this case, NFS has the highest intensity in the world for a particular range of energies from 1 MeV to 40 MeV. And what do we do with all this? So we have just started using this now. And in this year in September, we'll be doing the program approved experiments which an international committee chooses, and then those experiments will be done. So we will be doing material science studies which are connected to reactors, and we'll be studying fission and basic things and other interesting reactions which are useful. And then the other equipment that we have is the super separator spectrometer. Basically, what you want to do is again search for rare events. When the beam comes in, let's say about 10 power 12 particles per second, it hits a target. As you know, most of them go unreacted. So typically we have to find one of these nuclei in 10 power 11 particles per second, in 10 power 11. So this equipment gets rid of the stuff which you don't want, and then goes to the focal plane where you measure the reaction, the nuclei which is of interest to you. We can do various studies here which can measuring new properties in nuclei which is N equal to Z, but not here calcium, but much higher. And then you can do laser spectroscopy, understand the atomic physics of these nuclei far from stability. And this is how it looks. It's very complicated. It's still being built. It will be ready by the end of 2023. And one of the things which we talked about before is to look for super heavy elements, which is not the direct goal here, but it will be look for very heavy elements. And one of the goals of the super heavy elements search is to look for an island of stability, because as you go further and further away, as I said, the lifetimes get smaller and smaller. In these cases, they can be something like milliseconds. And the idea is to search for an island of stability, which is predicted, where the nuclei here are expected to hang around for many seconds. So this has still not been found here. That's why there is this search for Z equal to 19, 20, and so on and so forth. Then there is also another facility which is being built, which is called DESIR, which you don't want to go into details, which can be fed from S-cubed from here, and also can be fed from spiral beams, which we talked about before. And the basic idea is to study the ground state properties of these exotic nuclei and see what do we learn from that. And then just to give an example, what is high precision here? The precision that be measured of the mass of certain nuclei that we can do here is that we can measure it to the level of 10⁻⁹, 1 part in 10 power 9, which is equivalenting to measuring the mass, the weight of an Airbus, and then adding a P to it and seeing the difference. So that is the sort of accuracies that we can measure today. So I don't go into this. We come into the Segre chart, and we can do a lot of different things, which are a lot of fun stuff. And then we learn more and more stuff. And many of the stuff that we do here is also relevant to understanding the recent things like neutron star mergers, gravitational waves, and so on and so forth. That comes by understanding the equation of state in high energy collisions. And then we have the standard questions, and I said we can be useful to other people. Then the question is, what about tomorrow, which is what it is. That is for you to discover. So you are going to come out there and find new things and have tell people what it is and have more fun and improve the understanding of this field. So then I would summarize. I have 2 slides here. So this is an analogy with Ganil. So Ganil, it started in 1976. Most of you, the students, were not born at that time. But I remember distinctly in that time in 1976, when we had black and white TV, I distinctly remember the Voyager, which was sent to go out in space. Today, Voyager still is working, okay, after more than 50 years almost, and it has passed Pluto. It is out of the solar system, and it still continues to give signals. So we had this beam. So basically, Ganil is still going strong like the Voyager, and we continue to give information, do fun stuff. And as I said, this is Voyager's, the humanity's furthest journey. And basically, as you know, it has, we want to understand what goes on there by learning what goes on in the lab. And then I'm a big fan of movies, because from movies you can learn a hell of a lot. But like in your lectures, you have to be very careful and attentive, because if you don't pay attention rapidly, you may miss the main part of the story or the important parts. So in this movie, Morgan Freeman says that you need to go from evolution to revolution. And this is the goal at Ganil. And this also should be the goal for you in your future career as physicists or technologists. So then I would like to thank you all for your time, for listening to me, and hope you're not fallen asleep. And I would like to thank all my teachers who have made me, who have allowed me to reach where I am today, and will also make you all reach great heights. And please remember that the influence of teachers extends way beyond the classrooms and well goes into the future, as you can see in the case of me and many others. Okay, so then I would like to thank you for your time, and I will be most happy to take questions, both academic and others. Thank you.
Thank you very much, sir. So now the session is open for questions and comments. So people can raise their hands or write on the chat box, or just unmute themselves and speak. So waiting for the questions.
Congratulations, Naveen, for a very, very informative talk. You took us on a really grand tour of Ganil and everything about nuclear physics. And I'm sure many students must have been excited to pursue nuclear physics. So that is something which you have done today. I just question, like, how much time you allowed for industrial applications? Just, I want to know, because that is very important, I feel.
7% of our beam time is given to, so typically we run around 5,000 hours per year.
Okay, and you charge them, or what is the way you do?
Yeah, so yeah, they are charged, but we charge them a very little. We charge them around 1,000 euros per hour. Beam costs are typically 5,000 euros per hour. Okay, so it's a little expensive, and nuclear physics, as you know, is not cheap. But the good part is that research, especially in nuclear physics, is free in the sense no accelerator in the world charges the users to do science. And this is very, very important, and this needs to continue, and hopefully will continue forever.
Yeah. Thank you. Thank you.
So I think I would like to hear questions from my younger colleagues and not my senior colleagues, because my senior colleagues can always chat with me later, and we continue to chat, because even though I'm sitting in France, the connection with my colleagues is extremely strong. And
I mean, I have a not question, I have a query.
Yep.
See, when you are using the first cyclotron,
yep,
beam is goes to the first cyclotron. What about second and third one? Are they idle?
Yeah, so in the case when we do just low energy stuff, for example, like 5.5 MeV, we don't pass through the second cyclotron. We just have a straight path which goes to the experimental halls.
Okay. So that time second and third cyclotrons are not used.
That's right. So actually the fifth cyclotron is only used when you want to produce radioactive ion beams. Okay. Of the reaccelerated radioactive ion beams.
And बहुत धन्यवाद, बहुत अच्छी talk थी.
No, thank you for your kindness, but it will be only, I can only agree to that if I get some student questions from the students, which was the purpose of this talk.
Students, do you have any questions? We have
yes,
students who do nuclear physics projects also, like
Hi, Naveen.
Ram
I have a
Prasad.
quick question for you.
Yeah,
Myself,
please.
Sarah?
I just want to know this. You told in space electronic circuits are how radiation affects. I just quantitatively what type of effect people have observed, because as you also told, Voyager is still going, and after so many years it is still working. Then what type of exact radiation effect has been observed so far?
So one of the things the main thing that they look is the lifetime of the circuit working. So for this, they can monitor different aspects, the currents or other things. But what they actually do is that during an experiment, they come with various components, and they actually change the circuit to see how they can increase the lifetime. And the other thing, for example, which I didn't talk about, but with relation to radiation hardness. So for example, recently we had the group from Alice, which came. So by the way, for the younger students, Alice is one of the 4 experiments at CERN, which studies quark gluon plasma. So they came and they were studying some of the circuits. So there they were studying the effect of radiation on the clock frequency. So because as you know, they have to mark the events by a timestamp. So in this case, they saw that the clock frequency was changing, which I thought was pretty neat.
Okay, thank you.
With all the such a beautiful place you showed, one important thing was missing was the canteen. You didn't show us that.
No, the canteen is a very good one. In fact, my colleague, we just have a new contractor. In fact, my colleagues are now complaining that the food is too good and they're all putting on weight, which is a very, very rare case. Yeah. So if you agree, I would like only to hear the students now. Because I told you in the beginning of the talk, there are no bad silly questions, and it will happen that I may not have the answer.
Yeah,
So,
I think students are there. Asad, could you like to ask any questions? These are those who have taken nuclear physics as elective. So they are my students also, I can see. They have experimental techniques in nuclear physics, nuclear structures, all
Some
these things.
students are here.
yeah,
Ram Prasad, do you have questions?
You can ask him about the detectors,
Tara
everything
is
about.
also here.
I don't have any questions in particular, but like, because actually we had studied a lot about this. Like, ma'am had taught us this in our in our course. Can I have your email ID if in case I have like a few questions related to my career in nuclear physics?
Yeah, sure. Naveen@ganil.fr. Just my
could you
name.
type it in the chat? I think that would be
Sure. Anytime. So I saw Amit. How are you doing, Amit? Not seen you for a long time.
Yeah, it's nice to see you again, Naveen, after a long time. Yeah, I am not. I'm more or less sitting at home. I keep giving some lectures here and there, but I have stopped my active nuclear research now.
But you wrote a book. Yeah, thanks for sending it to me.
Yeah, but I'm happy that you like it, and I tell the students to your students to read that stuff. And if they have ideas, like I'm thinking of something further to write.
Sure.
I just had one more question actually. In like regarding the future of nuclear physics, how will machine learning be an important tool for further studies, or is like as a student, is it advisable to spend a lot of time, spend your time mastering machine learning to a certain degree?
Yeah, definitely. In fact, we have a big European project which we are asking EU for money between particle and nuclear physics. So one of the topics that we want them to fund is exactly this. So machine learning, in this case, we were talking about beam tuning, which more complicated is the machine. It's more complicated to tune. So we are talking about having how machine learning can be done and how from the existing data one can teach itself or even artificial intelligence for beam tuning. And the other thing where you can call it machine learning is also how you can recognize patterns in data, which we have tons of, so or petabytes of data, and also how we can analyze this faster. So one of the things I can tell you that being good at computation will always serve you very, very strongly. But that doesn't mean that you neglect other stuff.
Okay, hi, this is Rajiv Kumar from BARC. Rather, I would like to ask a very general question. What is that which inspired you to take up nuclear physics as your career?
So the basic question is very easy because my dad was working in DAE, Department of Atomic Energy. So that stood by default. But when I went to my bachelor's, I wanted to do chemistry. Okay. But then the teachers swung it the way. It's always because of teachers. Okay. And then, of course, it was continued at UDP with people like Professor Rangwala and others. And then, of course, all my colleagues, 50, I think a lot of them are here, and it is thanks to their enthusiasm and wisdom that I continued in nuclear physics.
Thank you, sir.
Naveen, I am Alok here.
Yep, boliye. I recognize your voice. Yeah, you
हाँ,
don't have to introduce.
Yeah, this
boliye.
this neutron for basic science, you are doing complementary to what is done at CERN for NTOF. Is it part of that, or is it? I mean,
No, it's
improve from the what is being done at
yeah,
CERN.
it is complementary. Also, the other main advantage is that there is no gamma flash, so you can do that some of the things much better here. But the energy is also sort of different, and
So
flux is
your
different.
start time is well defined, or what? Or something?
Yes. The detectors are not made.
So many of the alumni who have given talks in this series have actually continued to interact with the students in terms of online projects, and some of them are from outside India also. So do you have, can you suggest, do you have any suggestions for our students? What are the opportunities at Ganil for international students, for example? Or is it possible to engage them into this analysis of this huge amount of data that you talked about, sitting at home?
Yes, in principle, the answer is yes, but maybe we have to look at the logistics, because the basic point is that, I mean, the data is huge, but to understand, to analyze this data, one requires a lot of background. But I'm sure the students are smart enough to do it, and then we should discuss this in detail, not here, but at a later time.
Yeah. The way the others have done is they have given a short description, project description, and also what is expected from the student as the prerequisite. And then I circulate it to the student, and then I just connect them to the person. And from there, they just take it on. So if there is some group which needs students to analyze data or do some simulation kind of thing, and you can connect the students to them.
Yeah.
Or if you yourself have some project, then please let us know.
Yeah, sure. But anyway, I will get back to you about this.
Would this be available only for MSc students, or students who have just passed MSc as well?
No, even former students are doing these projects.
Okay, so.
Sir, may I know, you said hello?
Yeah, my name is Naveen. My name is not sir.
Yeah, Naveen sir, I'm Mamta Jain from IUAC.
Hi.
Sir, I want to know, you said recently the clock frequency changes under radiation.
Yeah.
You have tested some radiation hardness and things, and you found the timestamp changes with respect to the radiation because of that, because the change in frequency, clock frequency. Is that so?
Yeah, yes. It's not me. It's some of colleagues from Alice who had come. Yeah, it's true. It is one, because I was this I happened to know because I was passing by and I was chatting with them. But they do many more things which I'm not fully aware of. There are a lot of fun stuff in this irradiation stuff. And then since we are talking about irradiation, there is also about changing the properties of materials. Okay, one of the things which is followed also is how to increase the resistivity. I mean, the longevity of materials which go in the radiation environment. So that also is followed up partly at Ganil.
Then how in the space things are working properly if their clock frequency, because most of the things are working on the basis of clock only in digital electronics or whatever be electronic things working in a space.
So if I may just clarify, so the clock thing which I talked to you about was for the detector in Alice at CERN, where the intensity is huge. So the beam intensity is very large. So the number of neutrons and gammas that come out and charged particles is extremely high. Okay, so the effect to see the clock thing, you need a lot of flux, whereas in space the amount of radiation is much lower compared to that. So in that sense, but that's all I can say. I do not know much more about this.
Okay, thank you, sir.
Most welcome.
Hello.
Yeah, hi.
Hello, sir. My name is Shilpi. I was a PhD student at BRC and now I'm doing postdoc. Sir, just one small question. In the schematic diagram that you showed, we saw that for the highest and possible energy of the beam has to go through 3 accelerators.
Sorry, I can't hear you now. Hi, can you hear me?
Voice is not coming.
You can't, I can hear you. Okay, just a sec. Is it better now?
No audio.
No audio for me?
No, from the student.
Okay.
I think she lost connection because I don't see her name in the list also.
I just wanted to inform the students and other people that in India, rather in Bombay, there are many facilities where irradiation, material properties modifications can be done in Photia, Peloton, in Vashi we have electron machine. So they can approach us.
Yeah, just to add to Suresh's remark, just because it is abroad, it doesn't mean it's better. Let's be very clear about that.
No, even in India, people are guiding our project students.
No, I understand, but I just want to follow up on Suresh's comment because I think it's very important.
Hello.
Very, very important.
Hello.
Thanks, Suresh.
Hello.
Yeah, hi.
Sir, I'm Shilpi again. Sorry, my internet connection is very, very poor, I guess.
No problem.
Sir, I wanted to ask that in the schematic that you showed, we saw that for the highest possible energy of the beam, it has to go through three accelerators, which have so many turns. I mean, the beam has to go through so many turns.
Yes.
So how do you maintain a good flux at the end of the beam? I mean, before it reaches the target?
Because that is a pure accelerator physics. So the condition is that when you go into the accelerator, this thing, because the magnetic fields are there, which guide this. The magnetic fields are highly mapped, so you know exactly what field you should put. Okay, and when you go through this, so it is purely mathematical. Okay, so if you build the accelerator correctly, you measure the fields correctly, it has to go out. There is no question. So if it doesn't happen, it means something is not correctly aligned and your calculations are not correct. So it is in that sense, it's a rather trivial job. If it goes through one, going through the other is not that much of a complexity. And in our case, the transmission has to be greater than 95%.
It is greater than 95%.
Yeah.
Oh, that is great. I mean,
no, it's not a question of great, because there is a problem. If it is not, that means the beam is hitting somewhere and you are going to irradiate it. So then you'll decrease the lifetime of your machine.
So there is a quadrupole at each turn, because during the turn, especially, there is a lot of flux.
No. There is no, in the cyclotron, there's no quadrupole inside. Quadrupoles are in the beam lines.
Not in the cyclotron, but when the beam
in the beam lines, yes.
Yes. Okay. Thank you, sir. And that talk was extremely, I mean, I've never heard such a nice talk with virtual tour and everything. Thank you so much, sir.
Thank you for your kind words.
Sir?
Hi.
Sir, at the beginning of the slide, there was an image written yesterday on it. Was that reference to Beatles song yesterday?
Yes.
Oh, okay, sir. And there was another image written Bob Dylan on it. So was it reference to that as well?
Yes, but that was to show Professor Rangwala's writing. You should get the main point was Professor Rangwala's writing, not Bob Dylan.
Yes, sir.
I don't know how many of you have the opportunity to see him writing on the board. Huh?
Must be very good. That time mobile was not there. Otherwise, you would have taken the photos.
Exactly. Actually, I wanted to make a comment on that, because when I was preparing for this talk, I was trying to look for photographs and other things. I had zero, absolute zero. Then I was asking one of my classmates, my batchmates, do you have anything? Then he said, boss, in those times, There were no cameras. There were no mobile phones. So forget it.
Okay, if you had asked me, I would have provided something.
No, that's
Rangwala
different.
has been very
Sorry.
kindly. He wants to share his very precious notes on our website.
Okay.
And they are currently with me, and I'm trying to get them typed.
Okay.
But probably we should put them as they are, since the students remember his handwriting so well. So we'll soon be putting up all this together and put it on the department website. So he has some notes which have some rare calculations which are not found in the books, and we are going to compile them and put on the website.
Excellent.
So we have his handwriting with us. Yeah, very beautiful.
Professor Rangwala, do you have any questions?
Yes, I've been hearing. I've been hearing you, and I've been hearing that it makes me feel that I haven't wasted my time and life. Because there are people who remember me fondly. That's good enough. Even for my handwriting, if not for physics.
Yeah, the handwriting is just a minor detail. But of course, we remember you for physics. I still remember, many things. In fact, I have your notes. Huh? This morning I was trying to find it, but I couldn't find it. But I have them. Huh?
Oh.
Despite moving so many countries, I still have them.
That's nice to hear.
It's your words of wisdom.
Can Professor Rangwala come on video?
Okay, I'm on video. Hello, can you see me?
Yes, we see you.
Yeah, so I'm on video.
Yeah, thank you.
Right. Now, who was the person who wanted to see me?
No, I'm Dr. Suresh Kumar.
Hello. Yeah.
Nice to see you.
Nice to see you too. At least that you wanted to see me. Good. Most of the students don't want to see me. No, it's not true. It's not true.
That's not true.
That's not true.